Assalamualaikum and a very good day I bid to all. Today, we will be presenting our data visualization group project entitled Surface Rendering versus Volume Rendering. So my name is Aqilah Hanim Binti Taufik. Together with me are my group members Muhammad Anas bin Adnan and also Muhammad Amirul Fahmi. So what we will be presenting today is the introduction to our topic, the methods used, comparison, and also implementation. So, visualization is amplifying cognition with the use of computer-supported interactive and visual representations of data. Volume visualization, on the other hand, is the representation, manipulation, and rendering of volumetric datasets that is concerned with this way of extracting relevant information from volumetric datasets through the use of interactive visuals and imaging. The objective of this is to provide techniques for looking into volumetric datasets and also to improve visual understanding. Volume visualization is done using two approaches based on the portion of the volume raster set which they render. The first one is surface rendering or indirect volume rendering, and the second one is volume rendering or direct volume rendering. So, conceptual volume visualization framework. Sampled data is where input is a measurement, and then voxel space discrete becomes volume rendering, and analytical data is when the input is modeling and it becomes a geometric surface. So when geometric surface goes through the isosurfacing method, when geometric surface goes through the voxelization method, it will become voxel space, which is discrete. And when voxel space goes through the isosurfacing method, it becomes geometric surface. And both these methods will be used to volume rendering and also surface rendering, which creates pixel space, which is discrete.
For this volume rendering, direct volume rendering, it is an approach that allows user visualizing three-dimensional scale field. It is used in industry that produce the data set for analysts such as medicine, physics, and others. In this approach, user captures slice with a regular number of image pixels in the sequence and at a regular interval. The dataset will undergo regular volumetric data process where users sample the local area directly around each voxels or volume element. This is to obtain volumetric data and create a single representative value for the region. After the 3D dataset is captured, the dataset will be read as a 2D projection. However, the volume must first be defined in relations to the camera position in space. Then user need to define each voxel's color and opacity, typically using a RGBA transfer function. Volume rendering methods, raycasting. The value of each pixels in the image is determined by sending a ray through the pixels into the scene image of the volume rendering. The sample is interpolated from the voxel grid at each sampling location. Popular filter are nearest neighborhood, box, trilinear, Gaussians, or volume rendering methods. Splitting project voxels such as volume element on the rectilinear grid to the viewing plane. It approximates using a tiny polygon with a Gaussian texture whose color and opacity are based on the voxel's data and the volume transfer function. The projection is made for every voxels, and the resulting splats are composited on the top of each other in back to front order to produce the final image. Surface rendering. Nearly all 3D visualization challenge use either indirect surface rendering or surface-oriented rendering methods. Surface rendering works on the premise of segmenting and extracting certain area of interest from the volume and then transfer them into polygonal models. Surface-oriented algorithm fits a geometric primitive to data value before rendering the primitive. The detailed values are commonly picked from the ISO surface, which is collecting the data points where the scale field equals a certain value. The ISO surface form connected surface such as the air or skin or brain or bone boundary in a CT dataset in typical data sets from the medical or scientific applications. Surface rendering method, surface tracking. Surface tracking is a surface reconstruction process that construct a geometric surface from a volumetric dataset by following the surface of pixels residing on the surface boundary. The boundary is defined by a thresholding, classification, or surface detection process. Given a threshold value, a closed contour is traced for each data slice, and then the contour is adjacent slides. Adjacent slides are connected, and tessellations, usually a triangle, is performed.
So another method that used in surface rendering is isosurfacing. So isosurfacing is a surface representing a constant value of scalar function. So it is an operation that gives the scene output connected surface, such as a binary shell. So the characteristic of this method is it has meaningful ISO value, interest in 3D impression, and also shading that gives a 3D impression. So the common algorithm in isosurfacing are the opaque cubes, or known as cuboidal, the matching cubes, the matching tetrahedra, and diving cubes. Right. Next. So as for the comparison between the two approaches, which is the surface rendering and also volume rendering. So the first one is the the surface rendering use 2D surface that are rendered within a 3D space and object that appear solids. So as for the volume rendering, it is a data consists of one or more that is supposedly continuous fields in 3D. As for surface rendering, another one is the data is converted to geometrical primitive, such as triangle, which are then drawn. But the conversion through geometrical primitive may lose or disguise some data. As for the volume rendering, the entire volume can be rendered providing interior information. So we can see that the data is seen more directly and less likely to be hidden. So as for the surface rendering, it is everything which is a 2D surface is embedded in a 3D space. As for the volume rendering, a transfer function that maps the data into a volume of RGBA values. This volume is rendered directly using a variety of techniques. And lastly is when surface rendering, it is good for objects with a solid surface. So as for the volume rendering, it is good for objects with complex interior structure and solid boundaries. Alright, next. So the example of implementation of these two techniques, such as one of the example are the CT scan in medical fields. So the computer tomography, or as known as CT, is a medical machine that used to scan human body and also display into an image form. So it is a medical imaging method that employs tomography, where digital geometry processing used to generate a 3D image of the internal object from a large series of 2D X-ray image taken around a single axis rotation. So this CT scan uses both surface rendering and also volume rendering. Alright, next. Alright, in this, as for surface rendering method used in the CT scan, so the way surface rendering implemented in CT is that it set a threshold value of radio density which chosen by the operator, and then it used an edge detection image processing algorithm for detecting the edge of the surface. And then after detecting and scanning it, so a 3D image can be constructed into an image. Then the multiple models can be constructed from various different thresholds that allows different colors to represent each anatomical component, such as the bone, muscle, and also cartilage. So as for volume rendering method used in the CT scan, so the surface rendering, it only limited to display the surface that meet with the threshold density. So it will only display the image or surface that is closest to the scanner or viewer. As for the volume rendering, it allows a transparency and color to be used for a better representation of the volume shown using a single image. As for example, the bone of the pelvis, as you can see, it can be displayed in semi-transparent so that even at some angle, the entire image is not blocked by other bone and can see through. Alright. Okay, I think that's all from us. Alright, thank you and have a nice day.